I'm Alberto Vilariño. We are many Albertos here, so one of those. And I'm doing a PhD with Carlos San Miguel and Rodrigo Castellanos. And basically, I'm moving a bit away from planes, moving to road vehicles. And the idea is to use machine learning to develop those. Okay, that's the way around. This is a bit of what we are going to look today. And that then shouldn't be there. Anyway, basically, the aim of this thesis is apply machine learning to the vehicle aerodynamic optimization. And why vehicle aerodynamics is important? Mainly, three main keys is, on one hand, fuel efficiency, not only fuel, also battery. We want to reduce as much as we can drag, so we can either use less petrol or get more kilometers out of our battery. Then handling stability, basically the lift forces on the vehicle, depending on their distribution front rear, can make the vehicle to be unstable. That we don't like it. We want vehicles that are predictable and they don't do stupid things. And finally, noise reduction. Some fluid structures can create quite a lot of noise, which has been reported several times as a quite of not pleasant situation for customers. And this is what we want to do as aerodynamicists on the industry. What happened? Then you always have constraints. First of all, you've got your friends from design, and they will tell you, no, that's ugly. We don't want that. Also, you have to work with other engineering teams. You need the car to be cooled off, because if not, it can burn. Or you need to go off-road, so you need to keep certain planes clean. Or you need to package stuff. You need to make the people to go inside and move on the car, because it's not what you are doing. And here is where the big opportunity comes for AI. Basically, in the latest years, it has been speeding up a lot the time frames. The development of the vehicles are becoming smaller and smaller, especially on startup business, where they want to develop the car quickly to get funding rounds. So everything goes speeding up, and that is where we can go in. And we are not doing nothing new. But the aerodynamics development, we know how to do it. Some examples are here. No, I shouldn't do that. Sorry. Sorry for that. Here. So in the vehicles start here behind. In the 30s, it's one of the first vehicles developed aerodynamically, the Tatra T77. As you can see, they were clever enough to use aerodynamics as a selling point. After that, war came, difficult times, and when the war ended, there was no much of interest in aerodynamics. Many things learned during those complicated times were applied to vehicles, but not for aerodynamics, mainly for aesthetics. They put things on the cars. They put quite a lot of stuff, nothing looking to efficiency. One of the best cars from that time was the DS, the Shark, if you remember it. And you can see from the 34 to 55, that's 20 odd years, same CD, no improvement. Time passed by, things keep like that, and then in the 74, the Playmobil appeared. And that's important, because the reason why Playmobil appeared was because in the 73 they have an oil crisis, huge one, so they have to make the toys small. And the aerodynamic industry understand that as well. The car were consuming too much, they need to make them more efficient. So from the 70s, 73-ish, start development of much optimized vehicles. First one, the Audi 100 with a CD of 0.3. And later on the 89, the Calibra, amazing number, 26, amazing car. Then some of the first electric vehicles appear on the horizon, the GM EV1 with that very low drag number. And Audi didn't want to get behind, but this is not an electric car, this is a full vehicle, the A2, fully developed by aerodynamic people. And that time passed by, we've got the Volkswagen over there, XL1 with a very low drag number, but this is the interesting one. 2020, Mercedes launched the VQS, 0.20 drag vehicle. So as you know, or as you can see, aerodynamic development has been there. We know how to do it, but we need to make it much faster. So that's what we are going to do here. And we are going to do it with a bit of machine learning. The workflow that I want to explore and apply during this thesis is start with a given design. It's this guy over here, the driver model. Simulate it. The data out of the simulation will go to the AI agent. With that data, we will look if it's an optimal result or not. If it's an optimal result, happy days, final design. If it's not, we need to modify that geometry. We need to parameterize somehow that geometry. Check that geometry because, we need constraints around that modifications. If the geometry is valid, we keep the loop. If it's not valid, we go back and generate a new design. That's the big idea of what the system should do. And, that should be that idea. The three methods that I've been looking into, mainly two of them, is the adjoint method. That's what I started with. It works very well because it's quite independent on the number of parameters you use. It's very accurate calculating sensitivities, and it's also a powerful tool having that sensitivities, and it's able to do constraint optimization. However, you have to calculate the gradient. You need to access the full CFD code to be able to do this calculation, and it's a bit complex to integrate, and sometimes it struggles with continuous media. So I did that work with a cylinder, as you can see over there. And one of the main problems we've got here is also is not able to do a whole optimization. It's just for local changes where it's more powerful. So that bit has been studied, but for now we leave it on the side. Maybe we'll back to it later on, but not at the moment. Then the next step is having a look at genetic algorithms. They are expensive. They take a lot of iteration to work. Sometimes they are very slow to converge, but they don't require gradient. They do not. They do global optimization. You can use any solver. You don't need to go and see the solver. You could use a black box solver, so anything off the shelf will work on this kind of optimization. We can use many time post variables. It could work on active vanes, for example, for shutting the cooling, or in the shape. It's not extremely complex to implement, and it's hard to impose constraints. That's a bit of a down. So that is what I'm going to look in, or what I've been looking into now. And then the other bit is reinforcement learning. It's inefficient. You require tons of data to it. The rewards define it as a bit of alchemy, because you need to know quite a lot about it. But you can use or not gradient. It does as well global optimization. It learns as it goes, so as much as you use it, as better it will do. It can do many of the things, and that will be the future, where I tend to go. On this process of developing my thesis, I tried to run before walking, and that thing over there, I feel quite represented. I thought it was going to be easy. Maybe it wasn't. Nope. So the many challenges I face, in one hand it was the CFD. The simulations take time to converge, some converging issues. Generating the mesh is tricky, especially for traditional CFD. Then parameterize the geometry. It's tricky. How do you manipulate? What kind of Madre de Dios. Sorry. So basically, summary, many problems. So the idea is go for something simple, much more easier, and that take me to take X-foil rather than CFD, panel method, go for a airfoil rather than a whole car, 2D problem, and using HIGO as the genetic algorithm to be used. This is the quick and fast idea. we need, how HIGO and Xfoil are going to work together alongside with the CST. We've got the initialization there. We get parameters, generate the airfoils, do all this loop up to get the cost function sorted. Then we've got an exploitation system within HIGO where we redo that to refine the optimal. If it's good, we've got an optimal. If not, we start again applying the genetic operations. It did work, although you have some challenge that I have to sort. Initially, is validate the airfoils, make sure that they do not cross, that they are smooth and nice. Here are some, one of the errors I've got. Here it was kind of constrained, but over there it was to collapse over each other. And then also I need to constrain the space of design. For that, I analyzed the NACA 4 and 5 CST optimization. And then for the evaluation, the cost function as well, the evaluation is something like that for different kind of missions, let's say a single angle of attack, multiple angle of attack. With that, we got these results. First one is a mission with 12 different angles of attack, but much faster. So, yeah, so those are the results. Different angles of attack, one a single angle of attack, or both of them incompressible, and here we put some compressibility. Those are the results. They look good, could be better, and that's what we are working in. There we go. So lessons learned, this helped me to have a good overview of how all the systems should work, constraints and all that kind of things. We've got a paper to be going to Eurogen 2025 with Isaac, and future work, different things, and the main one is use the data from DriveNet, which is some work that is already done on the driver, and that's all. So thanks, quick one, thanks to Isaac for HIGO and all that stuff, and Javi for giving me a hand with all these other things.